Hello and welcome. In this video, we're going to take a look at the derivative of logarithmic functions. We'll start with the natural logarithmic function, and from there, let's see. We can probably just go and find the derivative of any logarithmic function of any base. Starting off with, what is the derivative of the natural logarithmic function? Well, actually, because of implicit differentiation, we can handle this fairly quickly. We don't even have to use the limit definition. We're just going to write out the function y equals natural logarithm of x. Now, by properties of inverses, that means that we must have e to the y equal x. And now, what we're going to do here is, since we have an equation involving x's and y's, we're going to take a derivative on both sides here with respect to x. On the left-hand side, the derivative of e to the y is simply just e to the y, but we'll have to apply the chain rule. Now we need to derive the function y with respect to x, but of course, y is equal to ln x. That's actually the derivative we're looking for. We don't know what the derivative of y is with respect to x, but we can certainly write that down in the notation of dy by dx. On the right-hand side, we're just simply deriving x with respect to itself. Differentiating x is just going to give us 1. And now we have dy by dx equals, well, 1 over e to the y. Now, we have this kind of issue here that once we've done some manipulation and changed the function to e to the y, well, we end up with e to the y in our final answer. But the good news here, we actually know since that y is equal to the natural logarithm of x, e to the y is equal to x, and we can plug that in to our derivative. And thus that gives us dy by dx is equal to 1 over x. And y in this case is the function natural log of x, so we've come up with a brand new rule. The natural logarithmic rule. The derivative of the natural logarithm of x is 1 over x, which is a great, easy derivative. Almost as easy as taking the derivative of e to the x. Now, what about if we change the base slightly? Of course, we could change log base b of x to a natural logarithm of x just using a change of base formula. And after we've done that little change of base, we can see we just have this constant multiple. Log base b of x is nothing more than 1 over the natural logarithm of the base b times the natural logarithm of x. A little change of base formula. Now, what we can do with this is now take the derivative and use the constant multiple rule. And that constant multiple, using the constant multiple rule, is just going to be multiplying the derivative of the natural logarithm of x. And that gives rise to the general rule for logarithms. The derivative of the logarithm of x with base b is simply just 1 over x multiplied by a constant logarithm of b, the natural log of b. All right, with these two rules now, we can now take derivatives of just about anything. And remember, there's lots of rules with logarithms that can actually help us to simplify before we take the derivative. The logarithm of products, quotients, and powers can sometimes be simplified by the properties of logarithms. Let's just try a couple examples. All right, here we got a couple examples. We have y equals the natural logarithm of 3x cubed minus 7x, and another question here with f of x that's definitely a much more involved looking logarithm. Let's just start off by seeing how we can apply the chain rule here for part A. So seeing as how we have the quantity y, we might want to use the notation dy by dx. And then applying the chain rule, the derivative of the natural logarithm of some inside function, we're just going to have 1 over that inside function. Now, we can't forget the chain rule. We'll have to take the derivative of that inner function now. So that gives us 1 over 3x cubed minus 7x. Multiplying by the derivative, we have 9x squared minus 7. Now, of course, if we want to simplify that a little bit, this is really just 9x squared minus 7 over 1. And if we multiply numerators and denominators, we can make this look a little prettier. Now this gives us kind of a nice pattern anytime that we have the derivative of the natural logarithm of some stuff in brackets there. you ever have the derivative of, let's say, the natural log of some quantity u with respect to x, then it's simply 1 over u times the derivative of u. And then multiplying numerators and denominators, we can simply write this as the derivative du by dx all over u. Or if you prefer function notation, then the derivative of the natural logarithm of g of x is simply g prime of x over g of x. Kind of makes for a fairly straightforward derivative whenever we have to apply the chain rule. Now, what about this function f of x? You can see we have the natural logarithm of quite a lot of mess in here. We've got a root, we've got powers, we've got exponentials, we've got quotients, and we've got power rules. And it might seem like this is just a little daunting at first, but we have some rules, some basic properties of logarithms that we can apply here. So let's not forget, with logarithms of products and quotients and powers, we can either split this up into the logarithm of individual factors added together, or a difference of two logarithms in the case of a quotient, or we can bring the power down in front of the logarithm. So let's just see how much simplifying we can do with the function first. And remember, if we're just simplifying f of x, we're not going to write f prime of x just yet. That step will only come once we start differentiating the whole function. So applying our second rule there, we see we have quotient. We can write this as the difference of two logarithms. And then using the first rule, we have a product, so we can split that up into two logarithms, but we'll have to distribute the negative sign across both. And just like that, we've eliminated the need for product and quotient rules. We still have several chain rules to go here, but we can still even work on those. Because we have lots of exponents, even this root of x minus 5 can be written as x minus 5 to a power of 1/2, and powers can be placed as coefficients in front of the logarithm. We can do the same thing here with x cubed. Now, we'll have to use a different property here for this last term. The natural logarithm of the natural exponential function should be inverse operations that cancel each other out. So if we have 2x, and we use the exponential function and the logarithmic function on that, we should have the cancellation so that we end up with just 2x. And we finally have something that looks easy enough to take the derivative, so we'll start that process. We can write f prime of x now, and we have a constant multiple of 1/2 times the derivative of log x minus 5. And don't forget the chain rule here, multiplying the derivative of the inner function x minus 5. But that's just 1. The next term, we don't need a chain rule. The derivative of log x is simply 1 over x, and a constant multiple of 3. And then we've got a power rule. The derivative of negative 2x is simply minus 2. We'll just tidy that up slightly. And there we have it. Something that may have involved a lot of work with product and quotient and chain rules has simply been broken down into only one remaining chain rule. Remember that anytime that you have the logarithm of some function of x, we'll have to use the chain rule here. Whenever you just have the natural logarithm of x, then we don't need to use the chain rule. Even in the case here where the chain rule, the derivative of the inner function was just 1, it's still important to remember to do that step. And that is it. So that's kind of handy with natural logarithms. They're not a very challenging derivative, but it is a little bit easy to forget those chain rules that come up in there. But we'll see how this can help us out when we have very difficult combinations of products and quotients. Sometimes we can actually use logarithms and implicit differentiation in order to make the process a little bit more straightforward. But we'll save that for later. Thanks for watching, and I'll see you in the next video.